Okay. So, for preparing the lecture of today, I went back to a book which I discovered recently. It has been written by Gabriel Piola in 1824, the first version, and rewritten in several forms. I think the best version is 1848, and there is a last version, 1856. 6 years after his death, his best pupil published the last version. It is important because his ideas, in my opinion, are very usual in presenting continuum mechanics, but not only continuum mechanics, also discrete mechanics in a unique framework. Actually, when Piola was publishing his papers, the dichotomy discrete continuous was violently debated in the scientific environment. Actually, atomistic theories are very old, and Democritus and Leucippus probably formulated them in a scientific way, but we have lost many of their papers. In 1803, Dalton gives the most evident proof of atomistic structure of matter, the law of multiple proportions. It is rather difficult to deny that matter is made of discrete entities if the number of grams of hydrogen which are reacting with different elements are always an integer multiple of a given quantity. It is clear that in a chemical reaction, if a given amount of hydrogen is producing final results, being bonded with other elements, it is clear that you cannot avoid to think that there are some elementary entities constituting hydrogen which are mixing with other elementary parts of the other elements for producing new chemical species. The problem, however, is always the same. How many of these discrete parts of matter are involved in 1 gram of matter? Because the number could be enormous, and this could make discrete description of phenomena rather difficult. Actually, the Avogadro number, which measures how many atoms belong to a given weight of a given element, was measured very late, much after the debate we are talking about. So it is clear that two positions, both of them, can be assumed, and one has to choose which one is more suitable. I don't want to talk about philosophy. I don't want to enter into arguments of the kind continuous is more fundamental, discrete is more fundamental. This has been very dangerous. Maxwell believed that continuous was more fundamental, and he conceived luminifer ether as a continuous body falling in the framework set by Piola for discovery, and they even imagined a mechanism, I mean, a set of rigid bodies moving under the action of springs, which were behaving as the luminifer ether. It is very, very dangerous to decide if most fundamental is the discrete approach or the continuous one. When you believe that you reached a final word in the field, rather for instance, discovers that without any doubt there are atoms in a layer of gold, then quantum mechanics is born, and continuum description of nature, which was thrown out, comes back once more in the picture. So, in my opinion, one has to assume the Epicurean point of view, which is the following one. I have a model, I describe a set of phenomena, and I'm happy. When I find other phenomena, I change my model. Okay? However, the poor Piola, when he decided to use a continuous description of the motion of continuous body, was violently attacked by the French school in the person of Poisson. This is another very strange thing, because we're talking about something which happened, say, in the first half of 19th century. So the controversy between Piola and Poisson, which has been erased by the French school because they don't want to admit they took everything from Piola's ideas without citing him. Okay? I don't know if they did it willingly or not. This is very difficult to say. The controversy between Piola and Poisson started because Piola wanted to describe everything in a continuous framework, and Piola, for philosophical reasons, decided that as physics is dictating the discrete nature of matter, the only possible description of matter is the atomistic one. And this was the point of view of Poisson, Navier, Cauchy. So the poor Piola was obliged to develop his ideas using both points of view. And in my opinion, he is the founder of modern homogenization techniques. Not only, most likely, he produced the first important steps towards numerical simulations. Actually, in the book of Piola, you find flowcharts describing something which is very similar to numerical code. He did it for answering to Poisson, because he wanted to prove that his point of view was perfectly compatible with Poisson's, and that his results were, in a sense, incorporating Poisson's. Now, why I'm telling you this? Not only because this is what I'm studying in this moment, but also because it gave me an idea for presenting this part of the subject in a very compact way, and we will be ready to open a window towards numerical applications, towards homogenization, and towards continuous description of deformable body theories. Okay, and what I believed to have elaborated myself in my teaching book some 10 years ago, I have found in the book of Piola. So actually somehow these ideas had reached me. Okay. So let us start with a reference configuration of a set of material particles. Now, this set of material particles can be a discrete set of material particles, or it can be a continuous set of material particles. Of course, now we could start discussing about the physical meaning of this statement, of this expression, discrete set of material particles, continuous. Let us talk about the model for the moment, the features of the model, and these features will describe eventually different phenomena. Okay, but we have a unique frame which allows us to describe different kind of phenomena, I think. Now, the idea is the following. You introduce a sigma cell partition of the domain D star, where you have defined a continuous function k. So you have a domain D star. Let us imagine it is a subset of the Euclidean three-dimensional space. Then you have a smooth boundary. You could ask me, what do you mean with smooth? I tell you immediately. I need divergence theorem. So for me, a smooth boundary is a boundary for which it will be possible to prove the Gauss divergence theorem. Okay? Then I introduce a length scale sigma, and I introduce a partition of the domain D star in a union of cubes. Of course, you have the parts of the domain close to the boundary. Here, for a given sigma, you will never get a cube. Okay? But in the requirement of regularity, you will include the fact that the existence of these not complete cubes at the boundary is not producing any mistake in the treatment. So in a sense, you could imagine what is done currently in numerical code. Your boundary, you cut in piecewise flat or piecewise spherical or a given shape parts. Okay. Now, in every node, you are ready to imagine to have placed a material particle. So, you have two possibilities. Either you imagine mass density distributed in the domain D star, or you may imagine your mass concentrated in the nodes. In the first case, you have a continuous description of your system. In the other case, you have a discrete description of the system. And you assume to have defined a key function which maps every point in the star into the Euclidean space of positions. Okay, you will not behave like Cartesian philosophers. It is very important for you to distinguish between the material particle and the position where the material particle finds itself in a given instant. You know, the horror vacui philosophy which stopped the advancement of physics and mechanics for centuries is based on the belief that if in a position there is no material particle, this position is not existing. Okay? In some books, modern books, where there is no distinction between material particle and position occupied by material particle, this ancient mistake is still present. So for us, we have a Platonic idea of the body, which is its reference configuration, this star, okay? And then we have a map chi, which places every material particle in the position where it is located in a given instant. Of course, when time is flowing, different positions are occupied by the same particle, which is very elegantly represented in the framework of functions. By the way, the maestro of Piola, Vincenzo Brunacci, was the author of a book of analysis, a mathematical analysis, which has been used in Italy for 250 years. And in this book, there is very carefully described the concept of a function of three real variables, dependent one, function of three independent variables, plus time. So you have x, which is the position in a given instant, of what? Of capital X, the label of a material particle, and t. So once you keep capital X fixed, and you let time flow, you have a different position of the same material particle. Okay? When you keep t fixed and you vary x, you find the position of different material particles of your body. Now, the most clever move by Piola, I believe, is that he introduces this continuous function key also in the case of discrete description of the motion. I will tell you in a later lecture that I've recently discovered that all papers by Mario Pulvirenti or Carlo Marchioro or Raffaele Esposito, the whole school of statistical mechanics is based on this Piola assumption. You have a continuous function which you assume is existing a priori, and then you locate a discrete set of material particles calculating this function in a discrete set of points. Which one? The nodes of your array. Okay, but I'm talking too quickly. This is an analytical trick which is used nowadays for proving theorems. Okay, so for instance, if you want to pass from a discrete set of material particles to its continuous description using an homogenization technique, you assume there is such a key. Then you develop your reasoning, okay, then you heuristically find the continuous version of your equations, and then you rigorously prove that when sigma is small, the discrete description tends to the continuous one. But I'm going too fast in this, so I simply give you a hint. However, here I tell you that if you consider the Pijk node, and for being romantic, I use exactly the notation of Piola. So instead of calling it epsilon, I call it sigma. If sigma is the small length scale which is characterizing the side of the cubes in which you are partitioning your domain, then the point Pijk is sigma I, sigma j, sigma k, where I, j, k are at tripod, are three elements of zeta. So in Piola you find zeta 3, the triples of integers, as a model for the set of discrete material particles. And the position xi, remark that, okay, maybe it is better if I introduce three indices. The position xijk of the material particle Pij is exactly this value. So for the moment, I want simply to tell you that in order to describe the kinematics of a discrete and of a continuous system of particles, you need to introduce a function k, whose domain is a subset of R3 and whose image set is the Euclidean space of positions, which is another three-dimensional space. And this function is represented in this way with the language of analysis, mathematical analysis. Okay. Next step. There are two different kinds of bodies: deformable and rigid bodies. Actually, the model of rigid body is so rude that it shouldn't, one should not use it. However, historically it has been introduced, and in some particular applications it gives some important results. So we talk about it, but we talk about it simply because for measuring deformation of a body, we need to say how it is not rigid. So the main idea for introducing deformation measures is the following. Where my body is not rigid, there it is deforming. And I need to find a way for measuring how much it is not rigid. I will soon transform this into equations. Okay. I have to say that the tradition of Idana School of Mathematics is this one. You start with a simple case, then you generalize it step by step. In the past I was criticized because I wanted to present everything from the most general point of view I could understand, and then I started particularizing. Now the story, what happened to Piola's paper proves that this is not very clever. Because Piola starts with rigid bodies, then he talks about fluids, then he talks about general three-dimensional deformable bodies, okay? But everybody stopped at the first chapter and wrote that Piola was treating only rigid bodies. So Ellinger is doing this, Truesdell is doing this. So, people are lazy, so it is much better that you start from the very general point of view, and then if somebody wants to read you, he has to suffer. Okay, if you try to be polite, they think, oh, this Piola is stupid. He's dealing only with rigid bodies. But the idea is very clever, because he starts introducing distance preserving maps, what are called isometries. Isometries were considered the most important topic for high school professors to get the teaching job, to get the job, to get the position. In Italy, for 40 years, you could never win a concorso for teaching in high school if you didn't manage to describe every property of isometries. And in Archimedes' books, there are many lemmas and theorems about isometries. So most likely, this is a very ancient knowledge. What is doing Piola, following Lagrange? It is formulating in an algebraic way this property. I have found this very elegant proof in his book. So, what is a chi which is preserving distance? Easy. The distance in the Euclidean space of key x1, key x2, so the distance between the positions occupied by the material particle x1, x2, this is equal to the distance in the material, let us call Lagrangian description of x1, x2. So the map key is not doing whatever he wants. It has to verify this property. Okay, this is a doctoral course, so I give you something to do, or I hope that you already know it. If you have an application, a map which is preserving distances, then this application is preserving inner product. This is not very difficult, you can accept easily. If you have triangles, and if all distances are preserved, a triangle in the Lagrangian description becomes a triangle in the Alerian description. The length of all sides of this triangle remain the same, and the angle remain the same. So if you remember that a possible definition of an inner product is between two vectors is the length of one, the length of the other one, cosinus of the angle between them, then it is clear that the vector, the material vector, is mapped in a vector of positions whose length is the same. Actually, what is easily proven with trivial Cartesian geometry is that the only possible distance preserving map is linear. Okay, so in the book I gave you in the references, you find easily the very trivial demonstration of this. But I want to show you something which may be of use for us. So, you may choose an origin in the Lagrangian description. You call it x naught, and you find that kx is equal to kx naught. If I said linear, I was somehow wrong. I should have said affine. So the generic map from defined in a three-dimensional Euclidean space into, we can have in n dimension, but anyway, in a Euclidean three-dimensional space into another Euclidean three-dimensional space, which is preserving distances, it is an affine function. So you have this structure where L does not depend on the chosen x naught. So you have a linear map, we can call it L, and you can think about it as if it were a matrix, even if this is a little bit dangerous, because it becomes a matrix once you have chosen a reference frame here and a reference frame here. And so if you change the referential, this matrix changes exactly in the same way in which the components of a vector change if you change the referential. Not exactly, in a more complicated way, okay? Okay, so I want to underline that the linear part of the affine function we are talking about is not a generic one when chi is an isometry. So, distance preserving applications are affine, and their linear part must be such that inner product is preserved. Okay? And this is very important for what we will do. So, the vector in the reference configuration, the material vector is given by this difference. This is the vector of position. The material vector is given there, and you have this formula. So, following a very old habit of denoting with capital letters everything which is living in the Lagrangian configuration, and with small letters everything which is living in the Alerian configuration, in general you have a vector small v, and you have a linear map which maps vectors in the Lagrangian configuration into vectors in the Eulerian configuration. I want to underline, you have to understand something which is very important. Here you have a vector space, the translations in the Lagrangian configuration. Here you have another vector space, the translation in the set of positions. They are two different vector spaces. If you mixed them, you are lost. The biggest problems in continuum mechanics are found because people are mixing these two vector spaces. Of course, you can try to identify them in a way, but this is very dangerous. Something is the set of material particles, something else is the set of positions occupied by these material particles. Okay, I will try to keep this difference always clear. So, I need to estimate an inner product. So, I write this way. W, inner product V, This is the inner product where? In the Euclidean space. This is equal to L capital W, inner product LV. This is always in the Euclidean space, okay? But this is equal to the inner product on the Lagrangian space. So this animal is equal to WV in the Lagrangian space. Okay? So I have this identity. Now, my problem is the following. I have a linear map L. This linear map is calculated on a vector. Then I calculate the inner product with another vector. Consider that this vector is in the arrival space. Okay? I ask myself this question. There is another linear map such that this equality is verified. One has to pay carefully attention because this is in the Euclidean space and this is in the Lagrangian space. So you already must think that L bar is mapping small vectors into big vectors. So if you want to have this equality, you can never say that L bar is equal to L, because L is a map from a given domain to another given set of images. This L bar you are looking for is traveling in the opposite way. Okay? Okay. Now, again, the answer is that for a given L, in some, of course, the inner product has to be well behaving. The vector space has to be finite dimensional, otherwise everything becomes a nightmare if the space is infinite dimensional. In the case of finite dimensional vector spaces, this application exists, it is unique, it is called the transposed of the previous application. We will see soon how it is represented in a given set of coordinates. So, an important warning. You can tell that a linear map is symmetric. That is, it is equal to its transpose only if L maps a vector space into itself. And even in this case, we will see, this is a little bit dangerous. Okay?
So you call this one the transpose instead of the adjoint?
You can call adjoint. The habit is to call it transposed for finite dimensional spaces and adjoint in infinite dimensional. But maybe, look, I agree with you. Let us call it adjoint. Okay? Okay. Now, for the moment, let us assume that you have learned that L star exists. And we will see it is very easy to represent it once you have blocked a reference frame here and a reference frame there. Okay? Why this is very important? It is very important because now you can write LW LV equal to W L transposed LV. Now instead of Euclidean, here you have to write Lagrangian, and this is equal to W V Lagrangian. Okay? Now, simple algebraic properties. This is equal to 0. Then you can factorize left W. So you get this way. Then you remember that the identity applied to V is V. Factorize on the right V. And in conclusion, you get W, comma, L transposed L minus identity applied to V equal 0. Okay? So we have intensively used Levi-Civita calculus in a sense, because we are representing using algebraic properties. Remember that I'm careful telling when I'm factorizing right, when I'm factorizing left, because for composition of matrices or linear applications with vectors, commutativity is not valid anymore. Okay. Which is that linear application such that once applied to the generic V and then calculated the inner product for W, you get as a result 0. Okay, the decadence of the Italian university can be measured by the fact that this is an impossible problem for 95% of students. I am very, I like very much this theory. The reason is that Capelli, who is the, together with Rouchet, is the inventor of a theorem 10 years after Piola. So imagine the poor Piola doing these reasonings without having the complete theory in his hands. Capelli has been the founder of the mathematics department of, mathematics school in Napoli. Capelli has been professor in Napoli University for 40 years, I think. So this theorem has been published in the Rendiconti dell'Accademia delle Scienze d'Arti in Napoli. There is a unique application, linear application, which verified this, and it is the null application. So you get that a linear map is preserving inner product if and only if it verifies this condition. Linear maps which are verifying this condition are called also orthogonal linear applications.
So before you go ahead, I mean, this was not the formula that Piola was using. I mean, you were telling us in a modern language, or?
Piola was writing all this, or Piola, component-wise. But this presentation, I mean, this theorem, Piola asked a student of his to do, and what I'm telling you has, in my opinion, was published for the first time in Piola's book. So the algebraic description of isometries is for sure related to the Pavia school of mathematics, whose head has been Piola for a long while, even if he was never a professor. He was so rich that he didn't need to be a professor. Okay? He writes in his book, this demonstration is already available only using geometrical arguments, introducing cosines and very complicated trigonometric theorems. Here I present you for the first time a purely algebraic argument. So, but this is not all, because what is very elegant is now the proof, which is crucial for all what we will do, of rigid body velocity formula. So, let us, and it is astonishing how he managed to do it component-wise. Actually, he was very clever. He wrote one line, and then he rediscovers all results, repeating mutatis mutandis the calculations for the other formulas, and he managed to construct a sequence of algorithmic operations whose result was leading to the final one. But he didn't manage to gather quantities into vectors and tensors. So it is astonishing. For instance, the first line of L equals alpha 1, alpha 2, alpha 3. The second, beta 1, beta 2, beta 3. The third, gamma 1, gamma 2, and gamma 3. And then he has to fight with these components. Okay, so let us assume that our body is moving. So you have that this is a function of time. So we can say that key of x and t for every instant is equal to key of x naught of t plus, now we call q the orthogonal map which we need. Remark that q is q of t. And then you have x minus x naught, which is time independent. This formula I met a few weeks ago in Piola's book, in component structure. He writes explicitly, this animal is time dependent, but there is no space dependence because x naught is fixed. This animal is time dependent, and here you have only the linear dependence on x, capital X. So you can derive, with respect to time, this animal. And you get, which is easy, v of x and t equal, you will soon see that this is not yet the Eulerian formula which you find in fluid mechanics. This is v0 of t plus q dot x minus x naught. Now remark that this is a very strange function. I believe that this is not only important because we will soon find the correct way for introducing the deformation measure. This is very useful because it gives you an idea of the strange animals we are dealing with. You have a field, V. This field is defined here, but the vectors are living here. The velocity field is a velocity in the space reference. So the independent variable capital X is living in the Lagrangian configuration, and V is a vector in the space. And this is written clearly in Piola's book. Piola then, what is doing? He tells you, I need a formula purely Eulerian. So what I do? I use again this element. So, minus, equal, okay? Then I multiply times, on the left, Q orthogonal. This becomes the identity, and I can replace inside. Okay. Now, here there is an elegant discussion about the abstract concept of composition. He assumes that K is an invertible function, so that there exists K minus 1. So here you get X minus X naught, okay? And here you get X. This is the Piola transport of the velocity, Lagrangian velocity field. Okay, it is interesting that I know that in Berkeley they are calling this Piola transport. How they know, it is not clear. I didn't tell them. When I spoke to David Stegman, I told him, you know, I discovered this and that. He told me, Piola transport. They know. So it's very strange how these ideas arrived everywhere. This animal is not the other one I wrote before. This animal is now living here. And this is the Alerian velocity field, which people in fluid dynamics is accustomed to consider. So this is a vector field which is mapping in every x, small x, at every instant t, the velocity of the material particle which in that instant is passing there. In different time instants, in a given position x, you can have different material particles. The miracle of rigid motion is that the formula is this one always, with this animal being a given time function. Of course, you need to follow it. If you want to know where your x naught is located, you need to know k of x naught of t, of course. So this is valid only in the time interval dt starting from the time instant t. I mean, otherwise you need to integrate it for getting the motion. Now, what is amusing? Talking about the intelligence of people, which is always the same in every moment of human history. Piola proves in 2 pages that Q dot Q transposed is skew symmetric. as we are using the powerful tool of Levi-Civita absolute calculus, we prove it in 2 lines. Imagine the nightmare. You need to represent Q in terms of the cosines and sines of Euler angles. It is a nightmare. However, this has to be said to PhD students, there are now, in this epoch, colleagues, scientists, who claim that absolute Levi-Civita tensor calculus is useless. And it is a crazy mathematical abstraction. And they write everything in components.
I don't think it's all, I mean, usually they don't even know what Levi-Civita calculus is, so I mean...
But they say it is useless.
They say
They say it is useless.
I told them
I can show you books. In the first line they write, we will write everything in components because absolute calculus is useless. And then they write pages and pages of formulas. The poor Piola had in his hands calculus first year, calculus second year, which we are learning now. He couldn't, because it was not available, study linear algebra. So he was using the standard trigonometric geometric tool for fighting. However, he conceived this algebraic proof. So you can start with this. Imagine Piola writing this component-wise. So you write 1 row, 1 column, and you know that in an orthogonal matrix, the columns or the rows are unit vectors and they are pairwise orthogonal. So the inner product is 0. So then you can derive this equality. So what you do? This is equivalent and it is easier. You find Q dot Q transposed plus Q transpose dot equal 0. Of course, here I am tricking. I am applying Leibniz rule for differentiation for composition of linear applications. So I am heavily using Levi-Civita calculus. Okay? Then you have Q dot Q transposed equal minus Q dot transposed, but this animal is equal minus Q dot Q transposed, because you already know that. Of course, I'm also tricking because I'm telling you a lot of. I'm using a lot of properties of the transposition operation we were talking about quickly before. So actually I could prove it in few lines simply because I'm using already available results. If you have the naked knowledge, then you need several pages of proof. Okay, so at the end, and of course we could check this, but Piola claims, here I give you the first demonstration of this formula using algebraic arguments. So maybe you can find a Russian who did it in the same years. I cannot check everything, but these and what nowadays is not yet very well known, we discovered that angular velocity is not a vector. This is another thing you should know. Angular velocity is not a vector. Angular velocity is a skew-symmetric tensor. Of course, you can, it is more or less the same age, Gibbs. Gibbs, from this equation, introduces the angular velocity vector. So we open another quick parenthesis. Everything, all details, I ask you please to read all details in the book I am citing, because all these technical details are very important, and of course I cannot go in all details, otherwise this course could be 200 hours instead of the amount limited we have, okay? What is very interesting is this one. There is an existence theorem. For every skew-symmetric tensor, there is a unique vector omega such that this equality is verified for every vector u. Where the cross means vector product. Actually, this statement is not so precise, because omega is, there are two omegas. There is one omega in the set of left-handed referentials, and another omega, which is minus the other one, in the right-handed referentials. So what happens is that if you remember from the catechistic rule you have learned, I hope, in physics first year, for building the cross product of two vectors, you need to use your right hand for finding the direction of the product. Of course, for being politically correct, one could say, why you are not using your left hand? If you change hand, you change the operation. Okay? So when you change the operation, you change the omega in this equation. So there is a unique omega for right-handed referentials, and there is another omega which is minus the other one. So in some books of physics they talk about pseudo vectors, which is an oxymoron, because a vector is something which is changing in a given way when you change referential, and you cannot say that no, there is a vector which is not changing like vectors. Okay, you believe that you are doing things simpler. Actually, you are doing things more complicated. I don't know how to translate in English, I will translate it later. There is a famous Neapolitan told, we have to keep our culture. Lo sparagno non è mai guadagno. You can never save something. Very difficult. I will tell it another time. I need to think how to translate this. Okay?
It's not gaining.
Saving is not gaining. Yeah, maybe this is a good one. So you believe that you are saving time. Actually, you are wasting all your future time when you are misunderstanding what you are doing. It is like a tree which you transplanted in the wrong way. It will start growing in the wrong direction. Okay, so it is very bad. And indeed, Piola, even if he was aware that with 3 only components you could represent this skew-symmetric animal, tensor, always used this denotation. He never abandoned this denotation. So this is the rigid body motion velocity formula, okay? Now, what is a deformation? A deformation is something which is not rigid. Now, this beautiful mesh you have introduced with a sigma which is small enough for every use, instead of using it for discretizing your system, you may use it for talking about the measure of deformation. Okay. To be honest, this is not so clearly written in Piola. In my reading of ancient books, I found it in Cosera Brothers, the first presentation of this, but even not so clearly as we try to do it now. So what is the idea? To be honest, even if I'm not so fond of Cauchy, this is very often called infinitesimal elementary volume, Cauchy elementary volume. So we can define in a continuous body a cubic elementary volume to be an infinitesimal volume if for the position of all the points belonging to it you can use the Taylor expansion for the placement truncated at the first order for every use. So for instance, if you are estimating the deformation energy of your body, and instead of considering the continuous formulas, you imagine that every cube is deformed in a homogeneous way using Taylor expansion, and instead of calculating integrals, you calculate Riemann sums, the error is negligible compared with the order of magnitude of sigma cube, if you are considering volume integrals. So, whenever you can replace in all your formulas to key of x naught plus, I don't change the tradition and I call it capital F 0, x minus x naught plus infinitesimals. So if x belongs to the sigma cube centered in x naught, or if you have chosen a node x naught and you have attributed to it a cube, okay, whenever this formula for all x, capital X, belonging to this cube holds, then you say that this cube is an infinitesimal Cauchy elementary volume of your continuous body. Okay? Now, which is your deformation measure in x naught? And now, all the work we have done gives us immediately the answer. Because if F0 transposed is different from identity, then your cube is being deformed. Now, what is amusing is that this deformation measure is clear in the head of Piola. So actually, with some details to be cleared up, the first deformation measure which has been introduced is a non-linear deformation measure. What is astonishing is that engineers claim that the linearized version of this deformation measure is more natural, while this one is more abstract. I have never seen a rigid motion linearized. Nobody is able to perceive the vector field V of small x equal V naught plus a skew-symmetric W. We can see big angles and big displacements. So this is the most natural deformation measure. This is green deformation measure. Cauchy was very good in trying to steal it. So sometimes it is called Cauchy green measure, but this is Green's deformation measure. Green was working more or less in the same epoch. So the preliminary work we have done for characterizing rigid placements not only will be very useful for describing the change of observers, because two observers are using the same meters and the same chronometer, so there is an isometry between one observer and the other. But it also gives us a very powerful tool for introducing in continuum mechanics deformation, a measure of deformation. Remark, this is a measure of deformation because we could increase Taylor expansion. And then we could be obliged to study higher gradients theories, which are available in number 75 of Piola's book, and they're forgotten for 150 years. They are available in Italian, in Google. You digit Piola, and you get the book from Piola in Italian. And nobody could read up to page 150 to discover that Piola was introducing also higher gradients of deformation. But we'll see how this is doing this, why he is doing this. Okay. Now, before proceeding, we need to tell what is done sometimes. First thing, you can decide that your body is a fluid. So you can decide that your deformation measure is ρ, the mass density in the Alerian configuration. There is nothing bad in doing this. Why? Because ρ0 determinant of F is equal to rho. Sorry, the other way around. Okay. And of course, determinant of F transposed F is equal to determinant F square. Okay? So a fluid is a particular material whose deformation is related to the square root of determinant of F transposed F. Actually, the determinant is not changing. It's not changed if you rotate the Eulerian configuration. Okay, so you get that this is determinant of F is invariant under rotation. Exactly. Okay, maybe I should be slower. We have to tell that laws of physics are invariant under change of observer. In particular, deformation has to be invariant under change of observer. This is also written very clearly in Piola. So let us, before closing this lecture, this point, but I prefer to complete this topic before stopping. What is an observer? An observer is somebody which is giving 4 numbers to every event. So if something happens, this observer says, this event is happening here, and he gives the 3 space coordinates of the location of this event, and it is telling when this event is occurring. So for everything which is happening, we have 3 space coordinate r of E and a time coordinate t of E. Okay? Now, of course, we could do very complicated stuff. Nobody among us plans to study how to build starships traveling at the speed of light, at least not up to now, and nobody plans to study what happens in the far galaxies in the universe. So we can assume that a good postulation for mechanics is based on Galilean invariance. What is Galilean invariance? It can be stated very easily. If you call contemporary events all those events which happen at the same time instant for a given observer, the first part of Galilean postulation for mechanics tells that being simultaneous is independent of the observer. So if one observer sees 2 events and he claims these are contemporary, so they are simultaneous, another observer observing the same 2 events claims they are simultaneous, the same. Okay? So the class of equivalence of simultaneous events is independent of the observer. This means that at the end, all observers can use the same clock at the same time scale. The second part of Galilean invariance is the postulate of isometry for change of observer. If I observe two simultaneous events and I measure their distance, another observer is measuring the same distance. Of course, this implies that the statement is more complicated. It is possible to choose for the first observer a unit of space such that its distances are the same compared with the first observer. Okay? So you understand why Piola is starting with the reasoning I have presented you. If R1 is the position of event E as measured by the observer 1, and if R2 is the position of the same event as observed by the observer 2, then I can say that R1E is equal to R0 to 1 plus Q R2E, where R1O2 is the position of the origin of the second observer as seen by the first observer, and Q is an orthogonal transformation. I don't repeat the derivation. If we calculate this derivative once more with respect to time, what we have already done, we discover Galilean compositions of velocities. So the Galilean law of composition of velocity is a consequence of the two parts of the postulate of Galilean invariance. Okay, now imagine to have a deformable body. You need to deform it, so you pump in it some energy and you get a deformed body. Do you believe that two different observers will measure different energy? This is clearly against invariance of laws for change of observer. In particular, if there were two observers measuring different deformation energies, you could build an engine producing energy from nowhere. Because you could ask one observer to deform, the other observer to recover energy, and the two observers could be linked to the same source of energy. Okay? So, the measure of deformation has to be invariant for change of observer. Now, and then we stop, you can understand why it is clear and it is important to distinguish between the Lagrangian referential and the Eulerian referential. the Platonic idea of the body is there. It is independent of the observer. So, if the first observer is measuring f of x minus x naught as the deformation of the small cube, the second observer is measuring q f x minus x naught, because you have to compose with this change of variables. And you have only one q on the left. This animal is left unchanged. We will see that here there are other symmetries living. Here you are having material symmetries who are living. I mean, what is happening, changing the referential here, is telling you what is inside the body, how the body is constituted. Okay? While the invariance with respect to the change of observer, this is on this left multiplications times q. Now look how this is elegant. F transposed F. When you have changed, the second observer is measuring F tilde. Then he builds his deformation measure. So he gets F Q transposed Q F. This is the identity. So the Piola green deformation measure is invariant under change of observer. So this is the correct quantity for measuring, one correct quantity for measuring deformation energy. Okay?
So you are sort of postulating that the material frame is sort of absolute.
Yeah, it is. It is. When you change this referential, imagine, we will try to see later, imagine that you have a deformation energy. The deformation energy must depend on F transposed F, because this is the deformation measure in first gradient materials. Okay? If the material is isotropic, then the deformation energy must be independent of every change of frame here in the Lagrangian description. What is a fluid? A fluid is a material such that for every change of reference here, even not orthogonal, but belonging to the group of unim, or the unimodular with determinant equal to 1, the deformation energy is not varying, which is equivalent to say what I said before, depending on rho, the Eulerian mass density.
Let me ask you a sort of stupid question. This means that if you go to relativity, then in principle you should have a rest reference frame from the material in a sense.
This is so-called rest referential for the body.
But then what you do with the photons that cannot be at rest?
What I do?
With the photons, I mean, with the light.
No, okay.
No, I mean, I did depend on what. No. I mean, it was just
no, there is a difficulty, a big difficulty. If the body is big enough, you don't have one rest reference.
All is close.
First, then photons are what? Particles or waves?
Maybe waves, I don't know, but anything.
So you want to do second, I mean, you want second quantization with relativistic effects. it is beyond the scope of my knowledge. No, the big difficulty of continuum relativistic mechanics is that if your body is small, then it is a material particle and nothing happens. If your body is big, a galaxy, but continuum mechanics is used for studying galaxies, then you don't have one rest referential, because the rest referentials are different. And then you have another problem, which is that your manifold has a matrix which depends on the distribution of mass. I mean, it is very complicated. I can conceive what we are doing in general relativity, but with phonons I cannot conceive. But the special relativity falls in this frame perfectly. It is enough to have a space-time with Lorentz transformation, and everything is done exactly the same. So if your body is small, then everything can be done. So a spacecraft, a spaceship, I think we can design. You need to change a little bit, but it is conceivable. But to study galaxies, it is another story. Okay, so we stop here.